Hello everyone and Bismillah. So in this video we are going to simulate the system with the proportional controller that we have designed previously. First of all, if you want to simulate any kind of a dynamical system, you have to start by simulating the plant, which is represented by a transfer function. So we will be seeking for a transfer function block. This is our transfer function block. Now we have to change the transfer function to match our plant's transfer function. We know that the coefficient of s squared was 1, the coefficient of s was 3, and the coefficient of s to the power of 0 was 2. So this is the transfer function that we had for our plant. And before going and simulating the whole system that we designed, let's just simulate the system without the controller that we designed. Let's just have a look at the response of the system without the controller we designed. We will be calling a step function in order to supply or give us the reference. I think the step function. It's actually a function that gives us a certain magnitude after a certain time. So after time 1, let's leave it like this, it will give us a magnitude of 1. And we have to form a closed loop formation configuration, as I said before. So we will add a summation block, and this summation block has to be having a negative sign in here in order to form a, let's call it a negative feedback, as it's called in the literature. Then we will have to add a scope in order to have a look at what's happening, how the response is behaving like. So this is our system without the controller, and yeah, let's just call this a plant. Now if we run this system, we would like to have a response of 1 with the rise time being less than or equal to 0.5. But is this what we are going to have? I don't think so, because we do not have a controller for this system. Let's just inspect this response. You see that at time 1 second the response of the system started to rise, but look, the steady state response of the system is actually less than 0.35, which is way less than the response that we are desiring or we are waiting for, which is 1. And in order to check the rise time of the system, we may activate these properties of the the scope. They will be giving us the exact information. So the rise time of this system is 1.586 seconds, which is way more than what we desired. So this system does not work correctly. Okay, because of this we designed the controller actually. Let's go back and add the controller block. So for the controller, since it's a constant, we do not need to add a transfer function. We will add a gain. Okay, we will add a simple gain in here, and we found the gain of our P controller, I mean K sub P, was found to be 10.96. Now this is our P controller that we have designed before. Just try always to remember that this is a physical quantity. This represents a physical quantity. It's the plant itself, while this represents the software controller that we are dealing with. We can play with this as we like. It's nothing in the hardware. We play with it to achieve the response we need. So let's just run this file again and have a look at the response of the system. Now, yeah, we can find that the rise time of the system is actually achieved. Now, the rise time of the system is less than half a second, which is okay. Now, everything is cool when it comes to the rise time. However, we look at the steady state response of the system and find that this steady state response of the system is actually, and unfortunately, not 1. It's almost 0.836 magnitude. But can we achieve a better response? Yes, actually we can, by manually tuning the controller we had designed. So this is our controller. If we rise the amount of this controller, the magnitude of this controller, we will have a better steady state response. Let's just manually tune it. Let's just put it to be 20 maybe. Let's run it again. What will we have from 20? Now that's cool. We are getting closer and closer to the steady state we want. You can see that the steady state we have now is almost 0.9. It's closer to 1. The rise time has been, decreased. It's good. Yeah, everything is good. Is everything good? Actually, let's just discuss this after raising or increasing the gain again. So let's put 50 maybe. Yeah, 50. So by putting 50, we will have, oh, that's nice. We are having something closer and closer to the desired amplitude, to the desired steady state response of the system. It's now 9.6 almost, but 0.96 almost. But look, when we were increasing this gain of the proportional controller, the transient response of the system is getting worse and worse. So what I mean by the transient response, it first of all increased the overshoot. So you can see that the overshoot of the system is from 1 to 1.4. So it's almost a 40% or more of overshoot. Then we had some oscillations when we raised the gain of the proportional controller to be more than, 40 or 50. We started to have some transient response, and this is not good in terms of efficiency of the system. So in order to get closer and closer, we may actually, closer and closer to the desired steady state response of the system, we may actually continue increasing the gain of the proportional controller, but this will not solve the problem without trade-offs. It will solve it with heavy trade-offs that we do not desire. So in this case, what will we do to compensate for these transient responses? What will we do to compensate for this overshoot, unneeded overshoot, and maybe undershoot as well? We will be dealing with these types of things in the upcoming videos. We will be designing PD controllers, PI controllers, and maybe PID controllers in order to get rid of these, let's call them parasitic effects of our controllers. Thank you for listening, and see you again.